Good morning, everyone. My name is Griffin Cullen, and I'm a project engineer that's been working for AECOM on FEMA-related work for about 5 years now. My presentation today is titled Somehow I Manage, Managing to and Understanding Steady and Unsteady Flow. This pilot project came about through a risk map program funded by FEMA Region 8 and aimed to take a look at the differences in steady and unsteady flow. With the increased prevalence of 2D models and the ease of modeling multiple different scenarios, these differences will become more and more important. I want to go ahead and caveat all this by saying that I am by no means the smartest person in the world, not even the second smartest. And when I started this project, I was thinking that I would run a few tests, grab some results, and then have some great recommendations that I can put in a pamphlet and every floodplain administrator would reference it daily. Of course, that didn't happen, and I stumbled into what could potentially be a master's thesis. So this could be a very technical presentation, but I'm instead trying to share what I've learned, and hopefully there are a few recommendations at the end that you can take with you. The purpose of this presentation is to introduce floodplain managers to these terms, steady and unsteady flow, and explore their impacts on estimating water surface elevation as well as the regulatory process. In college, I lived in a house of engineers, and we all had hydrology Monday, Wednesday, Friday at 8 a.m. Homework was always due on Fridays, and if you went to CSU, you know that on Thursdays there were some pretty good beer deals. So quite often on Friday mornings, I would have a stack of homework papers by my door to turn in, since they knew I would always go to class. So if you were like my roommates and commonly skipped a 8 a.m. class on Fridays, which I can't blame you for, here's some quick definitions of steady and unsteady flow. Steady flow is most commonly used in 1D applications and assumes that fluid properties at a point in the system do not change with time. A unit hydrograph for something like this would be a straight line, which you can see on the left here. Unsteady flow is more common in 2D applications and changes with time. A unit hydrograph for something like this would ramp up to a peak and then fall back down, which is what you can see on the right here. Next, I'm going to explain the different scenarios we took a look at to try and understand and identify trends in the different methodology. We selected two different types of streams. The first was the steep mountain stream. We modeled this geometry 4 different ways, with 1D cross-sections and with 2D mesh, both of which we modeled with and without a bridge. So we had 4 different geometries: 1D channel, 1D bridge, 2D channel, and 2D bridge. The second type of river we selected was on the other side of the spectrum, a large braided river. And we modeled this geometry also in 4 different ways: a 1D channel, 1D bridge, 2D channel, and 2D bridge. For our flow data, we selected representative hydrographs for each stream. For the steep mountain stream, you can see that we calculated an average unit hydrograph that peaks within 10 hours, whereas the large braided river, which has a much bigger watershed, peaks at about 50 hours. These unit hydrographs were calculated either by extracting from an existing HMS model or averaging a number of storms using gauge data. The peak discharge values applied to these unit hydrographs were the regulatory 100-year storms. So for both the steep mountain stream and the large braided river, we had essentially 8 different modeling scenarios. The main variables being whether it was modeled with 1D or 2D, steady or unsteady, and with or without a bridge. Here's a matrix of what each plan name was according to the abbreviations in the right column. I also want to note that we tried to keep as many variables constant throughout these runs. For example, although we were looking at steady and unsteady, we did use the same peak, one for the steep mountain stream and obviously a different for the large braided river. We also use the same Manning's values throughout the geometries. So we ran all these models, debugged, reviewed, and landed on some results that we were pretty comfortable with. So now to get to some results. We examined results at 4 test locations on each reach for each scenario. If you're lucky enough to be modeling in HEC-RAS every day like myself, you might recognize this figure from the HEC-RAS hydraulic reference. We used it as a guide for where to put our test locations, which was upstream of the crossing, well outside of the contraction zone, at the upstream and downstream faces, 2 and 3, and then downstream of the crossing, outside of the expansion zone. For the 1D models, it was pretty easy for us to extract results, but for the 2D models, we decided to draw profile lines in the same locations as the 1D cross-sections. The numbered sections on the right of the figure correspond with the upstream, downstream locations on the tables to follow. I've created these summary tables to try and best show the differences we're seeing through the methodologies. The first thing to note is that the values recorded in these tables are water surface elevation and velocity differences. And the next is that the comparisons were conducted to the 1D study plans. So where you see a difference of 0.97, this means that the 2D study with the bridge plan calculated a water surface elevation 0.97 feet higher than the 1D study plan, which you can see in my rough equation at the bottom. Looking at the 2D results, which you can see in the left columns, these water surface elevations average to a difference greater than the 1D study, but you can see that there are some inconsistencies. For the bridge plan, the water surface elevations are higher above and lower below. This could mean that the flow is getting caught behind the structure. And for the channel plan, the water surface elevations are a bit all over the place, but we could see higher water surface elevations above the structure, even though it's not there, because the mesh could be picking up nuances that the cross-sections could have missed. For the 1D unsteady, throughout, water surface elevations are lower, which is likely due to the volume differences between steady and unsteady plans. For the 2D unsteady in the right columns, the channel is consistently lower, which makes sense again due to the volume differences. But for the bridge, we're seeing water surface elevations higher above the bridge. This again could be due to mesh differences or differences in the bridge calculations versus the 2D connection calculations. Looking at the large braided river results, we see that they're generally pretty similar. The 2D study calculated average higher water surface elevations. 1D study calculated lower, but 2D unsteady also calculated higher, which is actually the opposite of the steep mountain stream. This could be due to how the water surface elevations were extracted from the 2D plans. Because we're comparing at cross-sections, for the 2D results, we looked at the water surface elevation at the channel. In large rivers such as these, if we were to average the water surface elevation, it could be lower than what we're viewing at the exact channel. So looking at the velocity for the steep mountain stream, across the board in this case, we can see higher velocities between 1D study and all the other methodologies. The biggest thing to note is that the 2D study, we see velocities that are consistently higher, between 8 and 25 feet per second more than the 1D study, which is pretty significant. For context, the velocities in the 1D study plan range from 7 feet per second to 14 feet per second. So in some of these areas, we're looking at velocities of 30 something, which is pretty big. Looking at the large braided river velocity, again, we see increases. But with the 1D unsteady, the velocities are minorly greater. In some cases, the differences are 0, and in others, like that 0.05 and 0.06, I might classify those differences as somewhat negligible in a stream this big. Again, in the 1D steady runs, we had velocities ranging from 5 feet per second to 7 feet per second in this reach. So generally, here are the trends that we saw between our tests. For the 2D study, we saw both higher water surface elevations and higher velocities. In some cases, we saw velocities that were 4 times as high as the 1D study calculations. For the 1D unsteady, we saw lower water surface elevations, possibly due to differences in volume, and again, we saw higher velocities. But as noted previously, these were relatively higher and could be due to differences in the finite volume calculation. For the 2D unsteady, we saw lower average water surface elevations in the steep mountain streams, but higher water surface elevations in the large braided rivers. Like I mentioned previously, the higher water surface elevations in the large braided rivers could have been due to how we extracted the water surface elevations at the profile lines. And here again, we saw that 2D unsteady calculated higher velocities. So these are some general trends that we saw in our test runs. It's very possible that if we were to look at other variables such as model detail or adjusting the Manning's values or looking at runs on multiple reaches, we could see something slightly different. But I find it interesting that the velocity calculated higher pretty much across the board. So next, I'm hoping to speak to how this information could be useful when looking at FEMA's guidance and regulation. I'm mostly going to speak to this through an example project. AECOM recently worked on a clomber on a mountain stream that was generally pretty hydraulically complex. As an overview, the effective model for this reach was a 1D steady model, and to better evaluate this area, we used a 2D study as well as a 2D unsteady model. And from these results, we were able to create a corrected effective model, which was 1D steady, using the information from our various 2D runs. So going back to the effective model, it was a 1D steady with 3 bridges and 3 parallel embankments. As a pretty standard practice, the cross-sections were oriented parallel to the embankments. And because of the road height, the entire left overbank, which is to the north in the figure, was modeled as an effective. As you can see, these cross-sections are very long, and modeling the entire left overbank as ineffective overestimated volume stored upstream. This essentially assumed that there was no overtopping of flow over the roadways. These generally were pretty conservative assumptions, which ultimately overestimated the 100-year inundation throughout this reach. To take a closer look at the hydraulics of the area, we evaluated it using a 2D unsteady model. This showed us that there were multiple breakout flow paths upstream of and between the bridges. You can see the direction of flow from the particle tracking in the figure to the left. These multiple flow paths ran parallel to the embankments. This also told us that there were exchanges of flow across the embankments. So we got a pretty idea of the multiple flow paths through the area, and we also noticed that this unsteady run calculated water surface elevations much lower than the effective. Because of this, we didn't want to just go ahead and run with the lower water surface elevations and call it good. Instead, we also ran a 2D steady model to try and establish what these different discharges were through the split flow reaches. All of this helped us to create a corrected effective model, which was 1D steady. We used the discharge values established in the 2D study analysis and incorporated the multiple split flow paths. I believe there are 3 that you can see running between the roadways. as well as reoriented our cross-sections perpendicular to those flow paths. Ultimately, this clomber was accepted by FEMA and is a good example of how these different methodologies together within the context of FEMA's guidance and their general favoritism to Unsteady. Here are some final thoughts. So here are some recommendations that I've gathered throughout working on this pilot project. 2D study may be more comparable to regulatory models and is ultimately what helped us the most with our clomber, as I described in the previous example. It allowed us to extract flow values through these split flow reaches while still allowing us continuity at the junctions. If we were to use the 2D Unsteady model for this, we would have seen discrepancies at the junctions due to the time to peak. 1D study could underestimate water surface elevations due to the volume differences between a steady and unsteady hydrograph. This application might be more applicable in urban settings, one with storage changes, rapidly varied flow, and could be more useful in a design setting. 2D unsteady may be more common outside of a firm situation, but as I described in the previous example, it was extremely helpful in establishing how flow can occur in many transverse directions, especially for a situation like our clomber, where it was extremely hydraulically complex. Specifically for our floodplain administrators and communities, I suggest that you know your models to the best of your ability. Similar to the example I just gave, if you're handed a 2D model that's calculating water surface elevations that are much lower than your regulatory model, maybe that should shoot up some red flags. Additionally, if you're handed a design that uses velocities that are much higher than expected, maybe the engineer could be using an over-conservative methodology. Finally, know your guidance. FEMA has their hydraulic guidance documents for 1D and 2D analysis, 80 and 81, that outline pretty well when certain scenarios are most applicable. And I'm sure as the hydraulic world shifts more towards 2D, these documents will be changing and updating. So, for those of you out there who are Office fans, hopefully you noticed that the title to my presentation is the title to Michael Scott's biography, the subtitle of which is The Definitive Guide to Learning Your Office and Becoming the World's Best Boss. Maybe through working together at conferences such as these, we can write a similar book, The Definitive Guide to Learning Your Floodplains and Becoming the World's Best Floodplain Manager. On this final slide, I've included some contact information from the partners involved with this pilot project. Thank you very much to Terry and Marta at CWCB. I hope that this presentation provided some helpful, if not interesting, information, and thank you so much for giving me your time.